Hello class, this is Dr. Anderson, and we are starting a new topic, acid-base balance. So just to remind you of some things, pH is the negative log of the hydrogen ion concentration in moles, and allow me to further clarify that that is the free hydrogen ion concentration. So there are lots and lots of hydrogen ions bound to proteins and various things, but the free hydrogen concentration is actually quite low, so that we have about 40 nanomoles per liter, and that works out to a pH of 7.4. We've discussed this in class a little bit. The normal range per the textbook Stolting is 7.36 to 7.44. We've discussed in class how others set the range as 7.35 to 7.45. The bottom line is that there's a very narrow range for a healthy hydrogen ion concentration. The reason for that is hydrogen ion is extremely reactive. It'll react with proteins much sooner than a calcium ion or a sodium ion or a potassium ion will. So when hydrogen ion is added to a protein, that process is called protonation. Why is that? Well, remember that a hydrogen ion has lost its electron, so all it is a proton. So another name for a hydrogen ion is a proton. So when we add hydrogen ions to proteins or to some molecule, that process is called protonation. When we remove the hydrogen ion, then it's deprotonation. And proteins are molecules that are highly protonated and deprotonated as the pH changes. So if we change the pH, then we change the protonation of the protein. Now let's say we have a protein with a lot of charges on it. Let's say a lot of positive charges. And the pH decreases, meaning there's more hydrogen ion. Those hydrogen ions will protonate that protein, and then those positive charges are gone. That will affect how the protein folds, and that will affect how the protein functions. The other issue is that calcium ion is an ion that often binds to proteins. However, hydrogen ion is more reactive. So, if you have a lot of protons, less calcium will be able to bind that protein. As calcium levels go up, that basically decreases the excitability of your sodium channels. Remember, those voltage-gated channels are very sensitive to the voltage environment around them. They will become less so. They're less likely to open. Now, on the flip side of that, if hydrogen ion concentration is very low, then those spots on the proteins that hydrogen might ordinarily protonate are unbound. And then calcium will come along and bind those spots, which means free calcium will go down. When free calcium decreases, that causes cells to be more excitable because the sodium channels are more likely to open up. So changes in hydrogen ion concentration affects protein structure and function, but it also has a profound effect on membrane excitability. So hopefully you learned at some point that an acid is a proton donor and a base is a proton acceptor. So for example, we have carbonic acid. When it donates its proton, it becomes the base form, which is bicarbonate. Here we have hydrochloric acid. Hydrochloric acid is considered to be a strong acid because it nearly fully dissociates, so it donates its proton and leaves behind a chloride ion. Ammonium ion is in the basic form. When it donates its proton, it becomes ammonia, which is a base. And here we have sodium dihydrogen phosphate. When that proton is donated, then we have disodium monohydrogen phosphate. So the monohydrogen form is the basic form. The dihydrogen form is the acidic form. And so when we talk about phosphate buffer, we're talking about these two pairs of ions. Now phosphate can be protonated further to make phosphoric acid, which is H3PO4, and it can be completely deprotonated, so it's PO4 to the -3. But in biological systems, we normally see an interaction between these two main forms of phosphate buffer. So when we talk about acid-base as a system, we can talk about 3 lines of defense. The first line of defense is the fastest, but also the weakest, and those are the buffers. Buffers, as the name implies, buffers the system against large changes in pH. The lungs are the second line of defense. They kick in next, and they are more powerful than buffers. However, our third line of defense, that's the slowest to emerge, but it is the most powerful because your kidneys can get rid of hydrogen and can save bicarbonate, and is a very powerful organ in face of acidosis. So a buffer is defined as the combination of a weak acid and a weak base. It's important to have both components because the weak acid could donate its proton to a strong base and limit the pH changes, or the weak base could accept a proton from the strong acid and limit the pH changes. So the acid and base form are shuttling back and forth, trying to maintain a constant free hydrogen ion concentration, and that is what stabilizes the pH. So our most important buffer, and it's found in the extracellular compartment, the most important extracellular buffer would be our carbonic acid bicarbonate system. So carbonic acid is the weak acid, and sodium bicarbonate is the weak base. So here's a specific example of how this buffering works. Hydrochloric acid is a very strong acid. It's going to dissociate into a hydrogen ion and a chloride. That hydrogen ion, when it becomes free, will contribute to a decrease in pH. However, the bicarbonate form of the buffer pair can take up that proton, get turned into the weak acid form, carbonic acid, and now we have carbonic acid and sodium chloride, and no free hydrogen ion to change the pH. Here is the opposite example where you add sodium hydroxide. Sodium hydroxide is an incredibly strong base. So hydroxyl will take away hydrogen ions. Well, our weak acid can donate a proton to our strong base, and now we have sodium bicarbonate and water. Again, we've not contributed to the free ion concentration, and that keeps the pH relatively the same. So you can characterize how a buffer pair behaves using something called a titration curve. So on the x-axis is how much acid or base you've added. So oftentimes what we add is sodium hydroxide. And then the y-axis is the resulting pH. Alright, so notice we're adding some base and the pH is going up, but there's a region here of adding a fair amount of base and having a relatively small change in pH. And then you get to this point and you add base, and holy Toledo, see how the pH goes up, and then it gets to the point where you can't really increase the pH anymore because we're at 14. Now, what the heck is going on? What the heck is going on is the molecule in question is acetate and acetic acid. So we start out with lots and lots of acetic acid, very little acetate. And as you add the hydroxyl ion, then acetic acid donates its proton to the hydroxyl ion and gets shifted into the acetate form. In this region, the shifting of the hydrogen ions is most effective. That is the most effective buffering region of this particular molecule. And you notice we have something called a pKa, and at that pH we're at 4.75. At this point, it means our buffer system is 50% acetic acid and 50% acetate. If you have 50-50 of your buffer, that is your strongest buffering capability. Now what happens as we add hydroxyl ion, you get to the point where you use up all your acetic acid, everything is in the basic form, and now when you add hydroxyl there's nothing to do buffering and the pH goes up rather precipitously. Now this might be an appropriate buffer for the urine. You don't want your urine to be less than a pH of 4.5. But clearly this would not be a good buffer system for the blood. So that's another thing I'd like you to appreciate about buffer systems. They're going to have a point called the pKa, and the pKa should be close to the pH that you'd like your system to be buffered at. So here we are in words. The pKa is the point at which the buffer is 50% weak acid and 50% weak base. So in the case of acetic acid, we had 50% acetic acid, 50% acetate, and that pKa was 4.75. If I were thinking about the phosphate buffer system, if I had 50% dihydrogen phosphate and 50% monohydrogen phosphate, the pKa would be 6.8. I don't expect you to know that. That's just something that I'm telling you to appreciate what a pKa is. And knowing the pKa of a buffer system is very important, because at that point it tells you when the buffering system is at its best buffering capacity. And if you were to add acid or base, the resulting pH changes would be very small. So we have other buffers, phosphate, so dihydrogen and monohydrogen phosphate. We have all kinds of intracellular proteins. So for example, hemoglobin in red blood cells is a very important intracellular buffer. In acidic conditions, when oxygen is low, hemoglobin is very good at binding up protons. That contributes to that Haldane effect we talked about under the pulmonary section. Your bone acts as a buffer. So when you add acid to the system, there are salts in the bone that will take up the hydrogen ion. That dissolves the bone. So a chronic acidosis is really tough on your bone. It can result in osteoporosis, but in the short term the bone helps you buffer hydrogen ion. And so there are a number of buffers. So every time we have a pH change, do we have to go through all the buffers? No, we do not. And the reason we don't is because we can use something called the isohydric principle. The isohydric principle means that all your buffer systems should be in equilibrium. So whatever the phosphate buffer system is doing, that's the same thing the intracellular proteins are doing, that's the same thing the bone buffers are doing, that's the same thing the bicarbonate system is doing. And because all the buffers are doing the same thing, we can just talk about one buffer system and then assume that all the other buffer systems are doing the same thing. So many of the examples throughout this presentation, I will use the bicarbonate carbonic acid system to demonstrate what I'm talking about. So here's another titration curve. So again, here we are on the x-axis, and we're adding hydroxyl ion. On the y-axis is pH. So you add hydroxyl ion to acetic acid. At the pKa, you're 50-50. As you continue to add hydroxyl, all of the acetic acid has then been converted into acetate, and then we've exhausted that buffer system. That gets us up to above pH 7. Here we have the phosphate buffer system. Now, as we add hydroxyl, we go from the dihydrogen phosphate form at the pKa, which is 6.86. We'd be 50% dihydrogen, 50% monohydrogen. That would be the best buffering capability. So phosphate buffer is a very important intracellular buffer and a very important kidney buffer. As we continue to add hydroxyl, we continue to shift the weak acid to the weak base. When we've exhausted our weak acid, then we've sort of lost the buffering capability. And if we continued to add hydroxyl, then the pH would go up a lot. Finally, we have the ammonia buffering system. There's our weak acid and our weak base. We add hydroxyl. The pKa turns out to be 9.25. So why would we use this system? Well, notice that at physiologic pH or down close to urine pH, ammonium would be in the ammonium form. So it would be in the protonated form. And what we're going to learn is ammonia can be very helpful for snarfing up little hydrogen ions and buffering the urine. So here's where I can introduce a couple of terms. Something like the phosphate buffer system is a titratable acid. I can take a 24-hour urine sample. I could titrate how much phosphate is in that urine sample, and that would tell me about the buffering capability. Ammonium is an interesting situation because your kidneys can produce ammonia and can produce in response to acidosis. You produce that ammonia snarfs up the hydrogen ions, and then you can sneak a lot of acid out into the urine. So some people call the ammonia-ammonium ion system a non-titratable buffer because your kidney actually produces this. So here's another example of how we can use a PK. So you have a local anesthetic, so something like Procaine would be in its protonated form and its deprotonated form. Well, if its pKa is 9.2, you could add a bunch of bicarbonate, put it over into its unionized form, get it through the lipid-soluble sheath, and then once in there, it would meet a pH of 7.4. It would be in its more active form, and then you could have the activation of the anesthetic. I don't feel like I said that very well. But instead of saying that again, we're going to talk about it in class, and I would love for the nurse anesthesia students to chime in and talk about how they do this clinically. Alrighty, so we can talk a lot about buffers. We also can talk about how your lungs help you compensate for pH issues. So a product of metabolism is CO2. You can add that to water, and in the presence of a very fast enzyme called carbonic anhydrase, we can produce carbonic acid. Carbonic acid then can dissociate into a hydrogen ion and a bicarbonate. So if you increase CO2 because of metabolism, CO2 will drive respiration through both central and peripheral chemoreceptors, and you could also produce hydrogen ion, which will drive respiration at the peripheral chemoreceptors. Then you would blow off the CO2, and that would help you fight acidosis. Now the thing that we need to remember though, let's say we add some acid to the system. That stimulates ventilation, and we blow off CO2, which brings this reaction to the left. So we convert our hydrogen ion into carbonic acid, then carbonic anhydrase helps us get that into CO2. We blow that off, and we help with our pH problem. The problem is, what happens as you blow off the CO2? The CO2 levels get lower and lower, and now you have less of a carbonic or a carbic drive for ventilation. As CO2 decreases, there's less of a stimulation for ventilation. So it's hard to fully compensate. Likewise, let's say we don't have enough hydrogen ion, and that inhibits ventilation. We'll decrease our ventilation, and CO2 will rise. As CO2 rises, we shift that into hydrogen ion, and that helps us with our pH. But what the problem is, as CO2 goes down and down and down, then we have less of a drive for ventilation. So we have a hard time completely correcting the pH. Now, thank goodness we have the kidneys. So the respiratory system can get things going, but it's the kidneys that really can finish off and help us maintain pH. So remember all the things your kidneys are doing. Your kidneys filter all your plasma except for the red blood cells and the proteins. Those are not freely filterable. You make this filtrate that's like the plasma in every way, except it doesn't have protein in it, so it's an ultrafiltrate. And then you move that filtrate through the nephron, and you reabsorb sodium ions, amino acids, glucose, sodium. Water follows osmotically. Then you go through the loop of Henle. You reabsorb water on the way down. You reabsorb electrolytes on the way up. In the distal tubule, you fine-tune sodium reabsorption. Your kidney is also able to get rid of waste, so organic acids and bases are secreted by active transport. The osmolality of your filtrate depends on how much you're stimulating ADH. If you have a lot of ADH on board, you will reabsorb a lot of water, and your urine osmolality will go up. If you're stimulating a lot of renin-angiotensin, you will stimulate a lot of sodium reabsorption and a lot of water reabsorption. That will decrease the volume of your urine, and you're doing this to regulate osmolarity and regulate blood pressure. So in the proximal tubule, we have a sodium-potassium, whoops, I'm on the wrong side. So here's the blood, here's the basolateral side, here's your sodium-potassium ATPase. We're spending ATP to generate a gradient. So when we have low sodium, sodium can come in, exchange for hydrogen. Where does that hydrogen come from? It comes from the carbonic anhydrase system. So this hydrogen meets a filtered bicarbonate, forms carbonic anhydrase, carbonic acid. Carbonic anhydrase gets us to CO2 and water, which can come into the cell, meeting a new carbonic anhydrase, getting us back to carbonic acid. That dissociates into a bicarb and a hydrogen ion. The hydrogen ion is secreted, and the bicarbonate is reabsorbed with the help of sodium. Later in the tubule, and we would find these cells in the late distal tubule, some people call that connecting section. I've alluded to this before in class that the distal tubule, though it's not that long, has very specialized regions depending on the kinds of cells. So late in the distal tubule and also in the cortical collecting duct, you're going to find some cells called intercalated cells. There are alpha intercalated cells, which we've talked about before. Alpha intercalated cells have a hydrogen ATPase. That hydrogen ATPase pumps out hydrogen, or pumps out hydrogen and pumps in potassium. And then we have a chloride bicarbonate exchanger, and chloride then can leak out. Now, how did the hydrogen get in? How did the bicarb get in? Well, the same way it got in the proximal tubule. It's coming in as CO2 and water. Carbonic anhydrase is turning it into carbonic acid. It's dissociating, and the bicarbonate goes across the basolateral side, and the hydrogen goes across the luminal side. This way we can really crank up the secretion and therefore excretion of hydrogen ion. Now, we have a second type of cell that you probably didn't talk about in any of your other undergraduate courses in physiology. We have a beta intercalated cell, and we don't use these all the time, but when we use them, it's because we have alkalosis. So, we have a potassium hydrogen ATPase on the basolateral side, or a ATPase on the basolateral side, and we're exchanging bicarb for chloride on the luminal side. Again, how did hydrogen and bicarb get in? It came in as CO2, it came in as water. It met carbonic anhydrase. It got turned into carbonic acid. And then that dissociated into a proton that was pumped out the basolateral side, and a bicarb ion that was exchanged for chloride on the luminal side. So I hope you can see why we would use these cells with alkalosis, because that would allow us to really increase not just our excretion of filtered bicarb, but we actually would be able to secrete extra bicarb if we had a prolonged alkalosis. So run-of-the-mill kidney, we're usually using those alpha intercalated cells, but we have these beta intercalated cells, and we can increase their activity during alkalosis if we need to. All right. Now, this is a picture from Vander. So we have water and CO2. Carbonic anhydrase gets us into carbonic acid. Hydrogen ion goes one way using an active transporter, and bicarb goes the other way by it's kind of facilitated diffusion. Bicarb is driving the transport. Now, what kind of cell is this? And where is it? Can you see that this is a alpha intercalated cell, and we would expect to find it in the late distal tubule or the collecting duct to fine-tune the urine in the face of acidosis. Now, I alluded to this before, but here's a slide that will address this issue. We use titratable buffers and non-titratable buffers to help us excrete hydrogen ion. Now, why do we need this help? Because hydrogen ion secretion is gradient limited. And when the pH gets to be as acidic as 4.5, you just can't sneak any more hydrogen ion into the urine. And you don't want to burn yourself when you go to the bathroom, right? So we use buffers to sneak in extra hydrogen ion. So we will have the dihydrogen form of phosphate buffer, and we'll have the ammonium ion. They're weak acids. They will snarf up those hydrogen ions, and they can sneak them out in the urine. So phosphate is a titratable buffer. Ammonium ion is non-titratable. And why do we refer it to this way? Because with acidosis, your renal cells can make ammonia from an amino acid called glutamine, which basically has 2 amino groups on it. So you can deaminate it twice, produce 2 ammonias, then those can either cross the cell or get turned into ammonium ion, and this is a very powerful way to sneak extra hydrogen. So if you read a question that asks you, does the excretion of titratable and non-titratable acids occur with acidosis, and that would be true, we would use all the buffer systems present in the kidney tubule, the titratable acids, and we would make additional ones, the non-titratable acids from ammonia, turn that into ammonium ion. Ammonium ion is charged and then trapped into the kidney. So on your typical day with your typical metabolism, you're secreting 50 to 100 millimolars of acid a day. But if you have acidosis, your kidney can crank that up through gene expression and upregulation, so you could get rid of 500 millimoles of acid. And remember, we have those type 2 or those beta intercalated cells. We also have the ability to get rid of quite a bit of base if we would need to. So here showing us some buffering by a titratable acid. So here's our monohydrogen phosphate. Here's our alpha intercalated cell actively transporting hydrogen. It meets the phosphate. It becomes the dihydrogen phosphate. It's then trapped in the filtrate. But because the proton is associated with a phosphate buffer, it does not exert pH. And we can still keep pumping out this hydrogen because we're keeping below the gradient limitation. Here shows us the non-titratable. So cells can take up glutamine. Glutamine can be deaminated, and then and remember, we can take carbonic acid. That acid can go on the ammonia and be exchanged for sodium, or ammonia can diffuse right through the membrane, then find a hydrogen ion out here, and then become ammonium ion. Anyway, if the hydrogen is in the form of ammonium ion, then it's not exerting physiologic pH, and then we can sneak more hydrogen ion in. So we'd see a lot of this going on in the proximal tubule. All right, now acid-base disorders tend not to be simple, but we're going to pretend like they are to begin with. And so if you want to know what somebody's acid-base disorder is, first you start out with the pH. What the heck's going on with the pH? Is the pH acidotic or is it alkalotic? Then you look at your other two values. You look at your PCO2 and you look at your bicarbonate, and you say, what in the world explains why I have this acid-base disorder? The other value might be completely normal. That would tell us we have no compensation or secondary responses. But if the other value is also changed. Maybe that value is contributing to this disorder, so we have something complex, or that other value is helping you with your compensation. So some people talk about compensation, other people talk about secondary responses. You also could calculate a base excess, a positive base excess or a negative base excess, and that would tell you, give you more characterization of someone's acid-base disorder. A base excess is defined as the amount of strong acid that you have to add to a liter of blood, and you have to standardize that for temperature and CO2 and protein and that sort of thing. That would return the pH to 7.4. So a base deficit or a negative base excess is what happens in acidosis. That's the amount of strong base that would need to be added to return the pH to 7.4. I have a formula in your notes that would help you calculate base excess, and there it is also in this presentation. So there might be reasons to calculate this at the bedside. If base excess is more than 2 milliequivalents per liter, then that person has metabolic alkalosis. If the base excess, or negative base excess is more than minus 2 milliequivalents per liter, then you have metabolic acidosis. We also have something called an anion gap. Now, our most common cation is sodium. We also could add in some potassium there, but that's about 4 millimolar. And then our common anions are chloride and bicarbonate. And when we add those things up together, we should have an anion gap of less than 12 milliequivalents per liter. And the thing is, there are all sorts of anions and cations that we're not measuring. We measure these main three. But if you calculate the anion gap, and there's something wrong with your anion gap, that indicates there's an anion that's getting added to the system that you didn't otherwise know about. So maybe you're adding lactate, or you're adding ketones. So somebody's in lactic acidosis, or they're in ketoacidosis, or they ingested some kind of acid. This can tell you what's going on with somebody's metabolic acidosis. If somebody has metabolic acidosis and their anion gap is not increased, or something's happened with their anion gap, they probably lost bicarbonate. They probably have diarrhea or something like that. But, if somebody has metabolic acidosis and they have a really big anion gap, then there's some acid being added to the system. And what could those acids be? Well, there's a mnemonic, and I don't have it in my presentation here, but it's in your notes, and I'm trying to remember that memory aid. It's called mud piles. So M stands for methanol, and U stands for urea or uremia. D stands for diabetic ketoacidosis. P stands for propylene glycol. So on. I can't remember what the I stands for. L is for lactic acidosis. E is for ethylene glycol. S is for salicylates, which is aspirin. Some people add, when you have muscle trauma and breakdown of muscle, that's rhabdomyolysis, and so then that changes your memory aid to mud pilers. So don't worry that it's not in the presentation here. If you look at your note outline, you will find all the kinds of things that can increase an anion gap. So, the short version is the anion gap is calculated using typically measured ions. We can make predictions about unmeasured ions, so sulfates and phosphates and those kinds of things, and calcium and magnesium and potassium. We could put all those things in there, but we use our three normally measured ions, and if we have a high ion gap and we have to maintain electroneutrality, there's some other anions from somewhere. Where did those come from? And they're coming from something like lactate or ketones. So that would tell you, that can help you say, oh, well, we have a metabolic acidosis. What could this be coming from? If it's a child, did they find the antifreeze and drink it because it's this, green and tastes sweet, and the kids don't know it's not something they should ingest? Or do you know the person's a diabetic? Or did the person have a grand mal seizure? Something like that. That can help you sleuth out what's going on with somebody's acid-base disorder. So you can use acid-base information to help treat things. So things like weak acid poisoning or weak base poisoning. So for example, with a weak base, phenobarbital is an example. So phenobarbital is a weak base, and if you had a patient, they came into the ER, they overdosed with phenobarbital, you can use acid base to help your patient get rid of that phenobarbital. You'd give them bicarbonate. You'd give it to them IV. Now that wouldn't change your plasma that much, but all that bicarbonate then gets filtered in the kidneys, changes the pH of the urine, keeps phenobarbital in the charged form, and you're going to pee that stuff out. You can do the same kind of thing with a weak base. So an example of a weak base would be amphetamine overdose. So if you had an amphetamine overdose, you'd be adding a weak base that would cause metabolic alkalosis. You'd give ammonium. Remember, it's kind of like an acid, so you'd give ammonium chloride. You're not going to change the plasma that much because of all the buffering, but all that ammonium in the urine is going to really acidify the urine. Then amphetamine is then in its charged form, and then you're going to pee it out. You're going to get rid of it in the urine. I'll leave that there. You can read about it in your notes, and I can address your questions about that in class when we get to this topic. All right. We also want to think about secondary disturbances or other things that will happen because your pH is off. So you have acidosis. That tends to depress the CNS because you have elevations in calcium. Acid will cause vasodilation because alterations in calcium, but also you'll get alterations in potassium, and that potassium will result in cardiac arrhythmias. Remember that as hydrogen ion is shifting in to access intracellular buffers, then potassium will shift out, and you're more likely to see that with metabolic acidosis. Alkalosis is going to do the opposite. It's going to cause excitability and seizures because the low hydrogen ion concentration also lowers the calcium ion concentration, and you get excitable. You'll have vasoconstriction. You'll also have dysrhythmias because of the hypokalemia, and you're more likely to have something like an ectopic focus because you're suppressing the activity of the SA node. And remember, with alkalosis, you'll have a left shift of the oxyhemoglobin curve, so hemoglobin will not be releasing oxygen the way you would like it to at the tissue level. All right, so let's go through some simple examples of acid-base disorders. Respiratory acidosis, you're not breathing enough. You're hypoventilating, and there could be all sorts of reasons why you're not breathing enough. You've had a drug overdose. You have COPD, and you've been given 100% oxygen. We can talk about why that is. You're in cardiac arrest. You have sleep apnea. You have a head injury that's damaged your respiratory centers. You have lung disease, and you simply can't breathe anymore. So you're going to try to shift hydrogen into cells to use your intracellular buffers. Your kidneys are going to try to secrete hydrogen ion and reabsorb bicarbonate ion. Your lungs cannot help you because your lungs are part of the problem. However, this person comes into the emergency room and the emergency room staff can help the person breathe. You would put them on a ventilator. But a ventilator would be a medical compensation and is not a physiologic compensation. And we can talk about that more in class. So let's look at this pH. pH is 7.32. That is acidosis. Notice that the PCO2 is high. So a high CO2 is causing acidosis. This looks like respiratory acidosis. Bicarb is around 30. So it looks like the kidneys have been trying to hang on to bicarbonate. This isn't the worst pH you'll see in your life. So it looks like there is some compensation. It's really hard for somebody to be fully compensated, but clearly this person's partially compensated, and you see signs of compensation. Let's see. Let's say somebody is breathing too much. If you're hyperventilating, you're getting rid of boatloads of CO2, and your pH is going to go up. The basic thing you're going to use is renal bicarbonate excretion, and you're also going to try to figure out why that person's breathing so much. Could be a panic attack, maybe they've overdosed on something, overdose on aspirin, some bacterial infections can drive ventilation. Some of the waste products from renal failure can drive ventilation, so you'd want to figure out why that's happening. But your kidneys are very good at getting rid of bicarbonate. So look here, pH is 7.6. Clearly that's alkalosis. You look at the bicarb, and the bicarb is normal. So that suggests that's not the problem. If we look at our PCO2, it's 25. So we have respiratory alkalosis, and there's no secondary response. I don't see any compensation happening here. Okay, metabolic acidosis. Either you've added acid, and we'd increase the anion gap, or you'd lose bicarb, and we would not increase the anion gap. So intracellular buffers, and this is when you'd really expect to see increases in potassium as you're trying to shift hydrogen into the cells. So you're going to access those buffers. You're going to drive ventilation and drive acid secretion and bicarbonate reabsorption. If you add acid, you're going to have a lot of breathing through the peripheral chemoreceptors. Some of that acid will get converted into bicarb. That'll drive at the central chemoreceptors. So you think about how your lungs are going to try to compensate, and then your kidneys will take over by upregulating your acid-secreting proteins, and you're going to reabsorb every little bicarbonate that you can. If you have metabolic alkalosis, you've either lost acid, so how could you lose acid? You could lose acid through vomiting, or you could gain bicarbonate, maybe you're hypovolemic. Maybe you have a chloride disorder. Remember, chloride and bicarbonate travel together in the last part of the kidneys. Or you've ingested some kind of thing. You've ingested a lot of antacids. You've been given a lot of citrate, which breaks down to a bicarbonate eventually. And maybe you had maybe you had metabolic acidosis, and then they gave you a bunch of bicarbonate and you overdid it, and now you're in alkalosis. All right, let's look at our pH. 7.48, so not the worst pH you've ever seen, but clearly that's alkalosis. Bicarb is really high, so suggests metabolic alkalosis. Now look at the PCO2, 55. So what is this person doing? It looks like this person is hypoventilating in order to increase their increase their PCO2 to help with the acid. So we have a pH that's not too bad and evidence of respiratory compensation. The kidneys will try to get rid of that bicarb as well. Okay, so normal values. So here's a table that we'll work through in class together. I also will have another activity. So I'm hoping with class we can just spend the whole time on acid-base balance and do a lot of application. I hope all of you that our nurse anesthesia students and those of you that are working in clinical settings and have seen various things, that you will share your expertise. We'll draw cells on the board, we'll go through some problems, and really learn how to think through some things. I'll also give you a couple of examples of mixed disorders and how that can happen. But otherwise, we're just a little under an hour here for the presentation. So I will end it here, and I'll see you in class.